Hello everyone, welcome back to my channel called Robotics Workshop, and today in this workshop I will talk about the pooling method, which is the second most important step in order to implement the convolution neural networks. And I will talk about this method in detail, like what is pooling and why we need pooling in the convolution neural networks. And we will also see about different type of pooling methods, and we will see when and which type of pooling method we need, and we will also see how we can implement each type of pooling methods. And I will also show you the Python implementation of each type of pooling method. So in order to learn everything, make sure you don't miss any points during this lecture, so watch this video until end. And the last thing, if you are new on my channel, on this channel I usually make videos related to the real life robotics and about the control methods, computer vision, machine learning and deep learning. So in order to join my crew, please subscribe my channel and also press the bell icon to get the updates of the new uploads. So here we go. So here is the block diagram for the convolution neural network. So the first thing is our input image here which is of size n cross n, and we need this image in the matrix form. After that we need to apply the convolution on this image, and after the convolution we need to apply the pooling on the convoluted image. And I have already talked about this convolution method in detail in my old video with the Python implementation. So if you want to learn about this video, I will put the link in the description for this video, so go there and watch about this convolution method. And today I'm going to just talk about this pooling method here in detail. But after the pooling method we also need to apply the activation function, dropout function and softmax function to get the classified outputs in the end. So we will see first what is pooling and why we need pooling. So pooling is actually reducing the feature map from high dimension to low dimension. For example, here is our feature map, which is of size 224 cross 224 cross 64. This is the height, width and the number of layers. So if we perform pooling on this feature map, we will get the new feature map with the reduced dimensions in height, width, but it has the same number of layers. So for example, in case of image, for example, here is our image. So if we perform some pooling is just like downsampling, so we will get the reduced image. So this image is just the best features from this image. This image is formed by taking the best features from this image, and the new image will drop all the unnecessary features and that we don't need in the training part in the convolution neural networks. So this is how it also helps us to reduce the computational cost. For example, in the next layer, if we perform the convolution on the image with the bigger size, it will take more time. So if we perform the convolution on the smaller image, it will take less time. So this is how pooling help us also in reducing the computational cost. Pooling is actually summarizing the feature map here, and how it can summarize. It can just get the first features from the map and summarizing it into the small box. And this method is more reliable and robust. So the next thing, we have different kind of pooling methods. The first one is the max pooling layer, min pooling layer, average pooling layer. So first we will talk about the max pooling layer. So what is max pooling layer? Max pooling layer is actually helps to get the most prominent features of the feature map or from the image. For example, here is our image or the feature map. So we have applied the pooling here of size 2 cross 2 with the stride 2 cross 2. For example, we have applied the pooling of size 2 cross 2, so we need to take the first patch from the image of size 2 cross 2. So we take the patch from the image of size 2 cross 2 here. So in the max pooling, we need to find the max element in this first patch, which is 5. So we will put this 5 in our output matrix here. So the next thing, we need to apply the stride. For example, here we have a stride of 2 cross 2. So the next thing, we need to move the 2 steps in columns. For example, this is step 1, step 2. After taking 2 steps, we need to again take the patch of size 2 cross 2 here, and then we need to again find the max element in this patch here, which is 3. So we will take this 3 and replace in our output matrix here. And after that, we need to move 2 steps in the rows. So this is our patch. For example, in the row, this is the first step, this is the second step. Then we need to gain the patch of size 2 cross 2 here and select the biggest element here, which is 7. So we need to take this 7 here in our output matrix. So again we need to move 2 steps in the columns. So this is 1 step, this is 2 step. and then we need to apply take the patch of size 2 cross 2, and we need to find the max element here, which is 4. So we will take this 4 and place it in our output matrix. So this is our new image with the reduced dimension of 2 cross 2. So we have also reduced the image from 4 cross 4 into the 2 cross 2. So this is how pooling actually reduce the dimension of the image from bigger dimension into the low dimensions by taking the best or the most prominent features from the image in the max pooling. So why and when we need to apply the max pooling? Max pooling is actually helps in extracting the low level features from the image, like edge, point and more sharp values. For example, here is our original image and its dimension is 1200 cross 1750. So if we apply max pooling, it will guess the sharp values from this image, and it will also reduce the dimension from 1200 to 140 and from 1750 to 200. So this is the new image with the sharp values with the reduced dimension. So in order to get the low level features or the sharp values, edges from the image, then we need to apply the max pooling. So the next method is the min pooling. Min pooling is the opposite of the max pooling. Here we are again applying the pooling size of 2 cross 2 and stride 2 cross 2, and it is used to get the most non-prominent features of the feature map, and the most non-prominent feature is the lowest value in the feature map. Again, we have to take the patch of size 2 cross 2 here, and we need to find the minimum element in this case, which is, for example, in this patch is 1. So we will take this one and we will place this one in our output matrix, and then we need to move the stride of 2 steps in the columns, for example 1 and 2, and then we need to again take the patch of size 2 cross 2, and then we again need to take the minimum element, which is 6 in this patch, and then we will replace this here in the output matrix. Again, we need to move 2 steps in rows 1 2, and then we need to take the next patch of 2 cross 2 and we need to take the lowest element here, and again we need to move 2 step in column 1 2, and we need to take again the patch of size 2 cross 2 and find the minimum element in the patch and take this minimum element out and place it in our output matrix. And here you can see min pooling is also reducing the size of the image into the low dimensions, and yes, and why and when we need to apply this min pooling method is actually used help us to get the most irrelevant features from the image, actually to extract the features which have low sharp values or the edgeless features from the image. For example, here is our original image. So if we apply min pooling, we will get the new image, which will actually get this image is actually built by getting the low sharp values from this image, and this is also in reduced dimension from this dimension. So this is when we need to apply the min pooling method. If you need the low sharp values from the image, you have to apply the min pooling method. And the next is the average pooling method. In the average pooling method is the same. Here we are applying the same pooling of size 2 cross 2 with the stride of 2 cross 2. This method is actually the average values of the element available in the patch of the feature map. For example, here is our first patch and we need to take the average from this patch. So we need to add all these elements 5 plus 2 plus 1 plus 3 and divided by the total number of elements, which is 4 here in this patch. So we need to divide this 5 plus 3 2 plus 1 which is 8 10 11 divided by 4 number of elements. So we will get this value and we need to put this value in our output matrix here. Again, we need to move with the stride of 2 1 2, and in the next patch we will again take the average, place it here, and again take the average in this patch, place it here, again take the average in this patch and place it here. And you can see the average pooling is also reducing the dimensionality of the image by taking the average features from the image. And when we need to apply this average pooling, it actually helps to extract the smooth features from the image. For example, here is our original image. So if we apply average pooling, so here you see the new image is with more smooth values, and this is also reduced in dimensions in rows and columns. So this is, if you need the smooth features from the image, you can apply the average pooling in this case. So this is all about the pooling methods, and next we will see how we can apply these pooling methods in the Python code. So to implement this method in the Python code, you need to open your terminal here, and the next thing, you need to open your compiler where you can write your Python code. I'm using the Jupyter Lab, so the Jupyter Lab is opening. So the next thing, we will implement our method here. So I have already implemented the convolution filter here, convolution method here, and if you learn the code step by step, you can watch my old videos. I will put the link in the description, so you can go there and watch and learn the code, and also learn the full implementation of this method and the concepts. So to implement the pooling, we need to create a new function here. We will type def pooling 2D, and inside this function we need 4 arguments. We need to perform pooling on the convoluted image, so we will pass the convoluted image inside this argument, and we need the pooling size here, and we also need the stride, and we also need the argument like which kind of pooling we need to perform, min, max or average. So the next thing, we need to fill this function, and first of all we need to create our output matrix with the right dimensions. And to find the right dimensions for the output image or the matrix, the formula is to calculate the row size for the output image. The formula is simply the row size of the convoluted image. So for this, it's the convoluted image dot shape and 0 and minus your pooling size and divided by your stride and plus 1. So this is the formula to calculate the row size for the output image, and to calculate the column size, you just need to replace here with the column of the convoluted image, and here also the column for the output image. The rest is the same. So now we will create the empty output image with the right dimensions. For this, we need to type here like output, for example, pooled image, and the dimensions for this image is here is shape, and it is of shape, here again row and column. So the next thing, we need to fill our output matrix here. For this, we need to write 2 for loops which will go through each pixel of our column or through each patch in the image with the stride. So we will need to create 2 for loops for I in range, for the row size, for the output, and for the columns j here, j in range of columns here. So now it will go through each pixel of the output matrix, and we need to fill our output matrix here, which is output pooled image. And in these for loops, we need to take care of 2 things. The first one is the stride, and the next one is the patch. We need to create the same size of patch as the pooling size, and in the next iteration we need to move the number of steps according to the given stride. So we need to take care here in these loops, and the formula for this is simple. Like to get the current patch, we need to get our convoluted image, and to get the right patch from the convoluted image, we need to type I, and the stride, the number of steps, 2 I into stride again plus pooling size. So this is how you can create the right patch with the right stride. And for j, it is going the same, so I am simply copying it here and pasting it here. You just need to replace I with j. So this is how you can get the right patch with the right stride in the next iteration. So the next thing, we need to find the max, min or average elements from these patch. So for this, we will use if arg is equal to, if we need to do max pooling, so we will simply find the max element in the current patch, and then we need to fill our output pool matrix. I am simply pasting it here, and we need to type here I comma j and is equal to np.max, and we need to give our current patch in order to find the max element in case of max pooling here from the current patch. And we will repeat this for the min and for the average here. And for the min, we need to type here min, and we need to type here also min to find the minimum value in the current patch and fill our output matrix. And for the average, it will do the same here average, and we will also give here mean. So it will fill the output matrix by taking the mean from the current patch, and in the end we have to return our output pooled image. That's it. Next, to test over this so the next thing, we are going to test our function, this pooling to the so for testing this function, first of all, I am creating a random image of with the same values here. I am creating a random array of size 4 cross 4 with the same values, and we will pass this matrix into our function, and we will see will it generate the same output. So this is how we can test our method. So here we will create an array. For this, I need to type simple np dot array, array array, and in this array I need to fill the matrix with the 4 cross 4 and with these elements. So the first row is 3 1 1 3, so here it will go 3 1 1 3, and the next one is 2 5 0 2, so here it should be 2 5 0 2, and the next is 1 4 2 1, so here 1 4 2 1, and the next last is 4 7 2 4 4 7 4 7 2 4. So this is our dummy image. So the next thing, we have to perform the pooling 2D on this image. So for this, you need to call our function here. So for this, you need to run this thing here, this, and we have one error here, unmatched. Where is the problem here? Okay, we have the integer. Okay, so we need to give here. That's it. And now we will run it again. Yes, now it is done. And the next, we will call our function here, pooling 2D, and we will give our dummy image here, and we need to give a pooling size of 2, stride of 2, and our argument should be here max. And the output from this function is our, we can simply write here output. And now we will print both matrices here. First we will print our original dummy image, and for this we need to type image, and the next thing, we will print our output here. For this, we will simply type our output here. So now if we run this, so you can see we have the same here, and the output is 5374. So if we compare with here 5374, it means our function is working correctly. So the next thing, we will perform this function on the real image, so on the convoluted image. And for this, I will simply pass here our convoluted image. Here I have already performed the convolution on my grayscale image. And yeah, one more thing, remember this function works only for one color channel, which is grayscale. If you have multicolor channels, you need to perform the pooling for each color channel. But we will cover this multi-channels method in our coming tutorials, but for one channel you can simply use this function one time. So we have already performed the convolution on our image. Next thing, we will perform this the output from the convolution filter. We will give the convoluted image in our pooling 2D, and we will perform the max pooling. And the next thing, to plot our figure, we are simply copying this here and pasting it here, and the output is simple over output image. And we will also print the size and see it will also reduce the dimensions of the original image. So this is print.shape, and actually this is our now filter image here, and the shape of the output here, output. So next thing, if I run this again, filter image is not defined, so we need to run this block here, and now we need to run this. here. Yes, so you see we will get a new image, and here you can see this is our convoluted image, the dimensions, and our new image is half of the size of the convoluted image here. So this is how you can see the max pooling is useful in reducing the dimensionality of the image, and also in useful to get the features from the image, important features from the image. And this is it. So if you perform the min, you can simply type here min, so it will perform the min pooling for you, and you see it will give you the image with the reduced dimensions, but this time with the different type of features from the convoluted image. So if we perform average, so you can simply give here average, and see it will give the smooth image from this. So this is how you can perform the pooling on the convoluted image. This is it for today, and in the next tutorial we will see how we can implement the other blocks, the activation functions and the softmax functions to get the right classified outputs. And after completing this whole series, we will implement our implemented functions for the MNIST dataset, and we will use this dataset to classify the digits from 0 to 9. So thank you, see you in the next tutorial, bye bye.